All right, this is the last section in Unit 5. This is 5.5. I can find the average rate of change, which we're going to abbreviate that because it takes a while to write that, AROC. So if you see AROC, A-R-O-C, we're going to think average rate of change. And we're also going to talk about making comparisons using those rates when we're dealing with functions. So the warm-up says, when we see the word rate, what should we think? Now, hopefully you know this. When we see the word rate, we should automatically think, hey, they're just talking about slope, and we're pretty familiar with slope. So slope is a fraction, so let's write fraction right here. Slope is a fraction that represents how steep a line is, and in which direction it slants. So we've been talking about slope for probably well over a year now. Learned that last year. And one of the big ideas that we've been studying is the fact that functions make shapes when we graph them. Functions make shapes when we graph them. And remember, the shape of that graph is a picture of all the points that make the function true. So when we plug those points into the function, they make it true. We graph it on the graph, and if we've got a point on the graph, then it makes the equation or the function true. Now, one of the most fundamental things that we can measure about the shape of a graph is how steep it is and whether it's going up or down. And we've talked about increasing and decreasing and stuff like that. And that's one of the reasons why we spend so much talking about rates. And remember, if somebody says rates, we're going to think slopes automatically. Now, knowing the rate at which a function is changing at a particular point, that is a really big deal in higher mathematics. But for right now, what we're going to settle for is finding the average rate, or in other words, the average slope, over a given interval. Now remember from the last unit that average rate of change was just the average slope between 2 points on a graph, and so we start off by thinking of this as a familiar formula. So when we talk about average rate of change, we're just talking about the slope formula, and the slope formula is y2 minus y1 over x2 minus x1, or better yet, since we're talking about functions, it would be f of x2 minus f of x1 over x2 minus x1. Now, the bottom of this in function notation is a lot easier to work with, but you'll notice the symmetry here and the similarities here. So we're going to do x2 minus x1 on the bottom, and then on the top we do f of x2 minus f of x1. Now, sometimes we're going to refer to finding the slope, or the average rate of change, as finding the slope of the secant line. Slope of the secant. And remember, a secant is a line that intersects a curve in at least two places. And you're going to see in just a second why the average rate of change for a function and the slope of a secant refer to the same thing. And we're going to look at this on example 1. So I'm going to slide down here. We're going to take a look at this function right here. And it says, draw the secant line on the given interval, then calculate the slope of the secant on that interval. So what we've got here are these 2 points right here on the interval from 0 to 2. And remember, these are in brackets, so we're talking about x values. So I'm going to mark this one as x1 and this one as x2. So we're going from 0 to 2, and it just so happens that the point right here is 0, negative 3, and the point right here is 2, 0. So here's what I'm going to do. I'm going to draw the secant line. Now, some people will draw the secant line and they'll extend it past there. That's totally okay. It doesn't matter. So if you wanted to go out here and out here, that's totally fine. What we're interested in is just the slope from here to here. Now, since we have a graph, let's go ahead and think of this as rise over run. So I'm going to go from this point to that point. So I'm going to go up here, and then I'm going to go over here. So we're going to rise 1, 2, 3. So that's rising 3, and then run 2. Whoops, run 2. Okay, so this is what we get. The slope on this one is 3 over 2. We did the rise on the top and the run on the bottom. This right here is the slope of the secant. Slope of the secant right there. Now, let's take a look at this one. Over on this one, we're talking about a different interval. So the interval now goes from 2 to 3. So this is the first x value, and this is the second x value. So the interval goes from right here to right here, and we want to draw a secant line. So I'm going to draw a line that goes right from here to there. Let me make that look a little bit better. So we're going to go from here to here. Looks like that. Now, that's pretty darn steep, and it, gosh, hardly goes away from that line at all. But let's take a look at this point right here. We're going to go from 2, 0 to 3, 4. So I'm going to go up here, and I'm going to go over here. So we're going to rise 4, and we're going to run 1. So if we write down the slope of this one, this is 4 over 1. So that means the slope of this is 4. So slope of secant is 4. I'll write it this way on that one. So lots of different ways we can write it, but what we're indicating here is that we've got these 2 points on the graph, and we're finding the slope of the line that connects the two of those. So let's take a look at C right here, and it says, what do you notice about the average rate of change on the two intervals? Or in other words, what do you notice about the slope of the secant on the two intervals? Well, this slope right here is bigger than that one right there. So they're both positive. So both positive, okay? But m equals 4 is bigger, so I'm going to put that in parentheses, okay? It's bigger than a slope of, what do we have here? 3/2, okay? And it says, what does this tell you about the graph on these two intervals? And does this match what you see on the graphs? Well, a slope that's smaller means it's not as steep, okay? And a slope that's really big means it's really steep. So what we're going to say here is we're going to say the graph is steeper. Now catch how we say this. The graph is steeper on the second interval right here, on this interval from 2 to 3. So it's steeper on 2 to 3 than on, the other one was 0 to 2. So steeper on this short little interval right here than it is on that interval there. Okay, now it says verify that B is the same as the average. The answer to B is the same as the average rate of change. So this was the slope of the secant, and we kind of found this visually by just connecting the two dots and doing rise over run. But what we want to do here is we want to check and make sure that if you plug this into the average rate of change formula, so the bottom is 3 minus 2, this is x2 minus x1, and this is f of x2 minus f of x1, do we get exactly the same thing? So we have 3 minus 2 here, and this is f of 3 minus f of 2. Well, the function was 2 to the x minus 4, so that would be 2 to the 3, because we're plugging in a 3, minus 4, and then minus, we want to make sure we have that minus here, and especially when there's more than one term here, we want to make sure that we put that in parentheses. So let's just double check and make sure. So I'm going to come down here, and what we want to do is verify, gosh, we should get a 4 out of this. So let's check and see what happens. Well, this is 3 minus 2, so we end up with a 1. And this is 8 minus 4. And then this is minus 2 to the second is 4. And then this is minus a minus 4, so that's a plus 4. And one thing I want you to notice, and this is a good thing to keep track of, this minus 4 right here was part of the function, and that minus 4 right there was part of the function. Because those are constants and I'm distributing through, those two are just going to cancel each other out, and I get an 8 minus 4, which is a 4 on the top and a 1 on the bottom. So what that means is the average rate of change, so the AROC on this one, the average rate of change is 4, and that is the same as the slope of the secant. So we're in good shape here. It kind of shows that the average rate of change and slope of the secant, we're talking about the same thing. So I'm going to slide down here, and let's talk about this part right here. This is a general rule, and this is where we get into kind of the vocabulary and the way mathematicians talk about things. If we use the word where is something happening, like we're on this interval, what interval, where are we, and stuff like that, then we're talking about x values. And if we use the word what when we're talking about functions, we're usually talking about y values. So let me give you an example. If we say where does the maximum occur, then we'd be talking about an x value. And if we say what is the maximum, then we're talking about a y value or an f of x value, okay? So let me put it off like this. Put it in a big set of parentheses like that, okay? So let's say, for example, that the high point was right here, and that point happened to be 4, 7 or something like that. Well, if we said where does the maximum occur, we'd be talking about at x equals 4. And if we were saying what is the maximum value, then we'd be saying it occurs at, the maximum function value is 7. Okay, so hopefully that makes sense. We're going to do a couple more on the backside. Let's go ahead and take a look at those. Example 2 on the backside says find the average rate of change, which we're going to abbreviate AROC, on each interval, then answer the questions given the fact that f of x equals 3 to the x minus 1. So here's our function right here. And we're going to find the average rate of change on this interval. Now, I sometimes like to write the bottom first, so I'm going to write 2 minus 0 here because this is going to be x1 and this is going to be x2. So we're on this interval. They're giving us the x values, remember. So then this is going to be f of 2 minus f of 0. So let's go ahead and calculate what those are by plugging in here. So this is going to be 2 minus 0, again getting rid of the easy part first. And then this is going to be 3 to the 2 minus 1, and then minus 3 to the 0 minus 1. So what we get in the denominator here is just a 2. And then we get a 3 to the 2 minus 1 would be 1. And then this is minus 3 to the negative 1. So we get 3 minus 1/3. Remember, the negative in the exponent means reciprocal. And then we're going to divide that by 2. So what I get here is, let's see, 3 minus 1/3. That's going to be 2 and 2/3, which would be 8/3. And then we're going to divide that by 2. Now, whenever we've got a fraction in a problem, we might as well think of the other numbers as a fraction. So I'm going to think of this as 8/3 divided by 2 over 1. Whoops, let me fix that. And then remember, we never divide by a fraction. We're always going to flip that over and we're going to multiply by the reciprocal. And then we can do a little bit of cross-canceling here. So the 2 cancels with the 8. We have a 1 here and a 4 here. So the average rate of change on this one is a 4/3. Okay, let's take a look at the next one here, and we'll set this up the same way. So I'm going to do 5 minus 2 here, and then I'll have f of 5 minus f of 2. And then in the denominator, we've got a 3. So we're going to plug a 5 into f. So this is going to be 3 to the 5 minus 1, then minus. And then this is going to be 3 to the 2 minus 1. So the denominator's a 3 here, and then we get 3 to the, this would be to the 4th, minus, let's see, this is just 3 to the 1st. So we get a, let's see, 3 to the 4th. That's going to be 81. And 81 minus 3 to the 1st, that's a 3. And then we've got a 3 here. Now, we might be tempted to cancel those. Remember, you can't cancel terms. You can only cancel factors. So let's go ahead and figure out what this is here. We end up with, let's see, this is a 78 over 3. And 3 goes into 78 26 times. So the average rate of change on that interval is 26. Okay, now it says, what do you notice about the two rates here? So let me slide this down here so we can see this. One thing that we notice is that they're both positive. So I'm just going to write both positive. So they are both positive. And one is a lot bigger than the other one. So 26, that's much larger than this right here. This is only like a 1 1/3. So that's not very steep. So 1 is much bigger. 1 is much bigger. Now, what does this tell you about the graph? So we've got a couple of intervals going on here. We've got from 0 to 2, and then we've got from 2 to 5. So on the x-axis, we're going from 0 to 2 on part A, and then from 2 to 5 on part B, and we're finding the average rate of change. Well, the average rate of change on this first interval is about 1 1/3, so it's pretty steep, maybe a little bit steeper than that indicates right there. But 26 would be ridiculously steep. We'd go up 26 and over 1, so that would just be ridiculously steep. Okay, so we're going to say this, much steeper on the interval from 2 to 5 than it is from, whoops, let me close that off with a square bracket, on 2 to 5 than it is from 0 to 2. And that's enough of an indication that we kind of know what's going on with those two. So let's slide down here and let's take a look at this next one. It says, find the slope of the secant on each interval, then answer the questions given the fact that f of x is negative 3x plus 1. Remember, if we say slope of the secant, what we're really talking about is the average rate of change. So there's really no difference between the two of these. I am going to put an m here because we're finding a slope there. We could have done the same thing on the other one. So again, I'm going to do 4 minus 1, and then we're going to do f of 4 minus f of 1, and then we're going to plug these values into the function. So I get a 4 minus 1 on the bottom, that's a 3, again, getting the easy stuff out of the way. And then this is going to be negative 3 times 4, and then plus 1. And then do yourself a favor, when we subtract this second part, put this in parentheses. If you do that, you're much less likely to make mistakes. It also leads to some interesting things down the road with more complicated expressions. So we're going to have negative 3, and we plug in a 1, and then plus 1. So this right here is f of 4 because we plugged a 4 in, and minus, this is f of 1 because we plugged a 1 in. And let's see what we get here. So we've got the 3 in the denominator. This together, this is going to be a negative 12 plus 1. So negative 12 plus 1. And then this would be a -3 plus 1. And I'm going to do something kind of silly. I'm going to distribute this through here. So this ends up being a +3 and a -1. And then you'll notice that we can cancel the two of these off. And I end up with a -9 on the top, a -9, and then a 3 here. So we end up with a -3. So the slope there is -3. So we've got our answer on that one. Let's do the same thing for the interval from 0 to 2. So again, the slope is going to be, I'll do a 2 minus 0 here, then we're going to do f of 2 minus f of 0. Again, same calculation, same process every single time. So the denominator is going to be a 2 here. We're going to plug a 2 where there was a 4, and we're going to plug a 0 where there was a 1. So I'm just going to do -3 times 2 plus 1 minus this stuff in parentheses. So this is going to be -3 times 0 and then plus the 1. All right, so let's see what we get here. This is a -6 plus 1. That would be 0, and then this would be -1. You'll notice that the 1 and the -1 will cancel each other off, so we'll get a -6 over 2, and we end up with a -3. So the answer on that one is also -3. Now, down below it says, what do you notice about the two slopes? Well, the two slopes, they're exactly the same. So exactly the same. And like before up here when we noted that they were positive, let's just write down that they are both negative. So in this case, they're both negative. All right, so what that means is we've got a slope of -3 on one interval, and then we've got a slope of -3 on the other interval. They're both exactly the same. And what does this tell you about the graph? Well, what this tells you about the graph is it's going down. It's going down, which means it's decreasing. Decreasing from left to right. And this is the important part, at exactly the same rate. At exactly the same rate. So if you think about it, what this means is we've got this graph that on the interval from, what do we have here, from 1 to 4 and from 0 to 2. So from 0 to 2, it's going down at a rate of -3, and then from 1 to 4, it's going down at a rate of -3. So it's a straight line, and we can kind of tell that by looking at the function. This is a linear function, so it should go down at a straight line. So it kind of confirms something that we already know. So if we go ahead and take a look at this right here, it says find the average rate of change and make comparisons. Do you feel like you can do that? Do the self-assessment, and let's take a quick look at one problem from the assignment. So we're on the back side of the assignment. This is problem number 7, and it says find the slope of the secant on the given intervals and then answer the question. So similar to what we did in the notes. I do want to take a quick look at this one and show you a nice nifty little trick that's going to come in handy in the long run. Remember, when they say find the slope of the secant, it's still the same as finding the average rate of change on an interval. So I'm going to set it up like this. We're going to have 3 minus a -2, and then we're going to have f of 3 minus f of -2. So let's see what happens here when we do this. This is 3 minus -2, so this is going to be 3 plus 2, so that would be a 5. And then we're going to have what we get when we plug in a 3. So this is going to be 4 to the third minus 3. And then again, write a minus, and then like we had before in that last example in the notes, we've got more than one term here. So I'm going to put this in parentheses, and we're going to plug in a -2. So this is going to be 4 to the -2 minus 3. Now, what a lot of people would be tempted to do is go ahead and evaluate each one of these, evaluate this, figure out what that is, and then go ahead and subtract them. But I want to show you what happens if I distribute this through. So this is going to be 4 to the third minus 3. Again, we've got that 5 in the denominator. And then this is minus 4 to the -2. Again, when you distribute here, it doesn't have any impact on what the exponent is. So it just becomes subtracting 4 to the -2 rather than 4 to the -2. And then minus a -3 is going to be a +3. And now notice what happens here. This is a -3 and this is a +3, so the two of those are going to cancel each other out. So what we have here is we have 4 to the third minus 4 to the -2 divided by 5. This is 64 minus, and remember -2, that's going to be the reciprocal, so that's going to be 1 over 4 squared, so that's going to be a 16th, and then we have over 5. Now, it's not that you can't plug this into a calculator. In fact, it might be a good idea to do this in a calculator. But the point here is you can do a whole bunch of this work and a bunch of this simplification very easily, and you can make this a much simpler problem by just thinking, hey, what I've got now is I've got 63 and 15/16 divided by 5. If I wanted to change that into an improper fraction and then flip the 5 over and multiply by its reciprocal and stuff like that, I could. You can also just type that into your calculator and it'll give you a nice little fraction for that, because remember, we're trying to find a slope. We want to make sure that we've written those as a fraction. All right, good luck with the assignment.